ya untuk pagi hari ini bisa coba di-input ya, mudah-mudahan tidak ada masalah untuk menginputkan kode. Baik, semua sudah memasukkan ya. Oh masih belum, oke baik kita tunggu aja dulu. Baik ya, sebelumnya saya mohon maaf ya terpaksa membatalkan kegiatan offline kita begitu ya, karena ini qadarullah juga anak masih belum fit betul ya, jadi memang sudah beberapa hari sakit, harapannya hari ini tadi sudah baik ya, tapi ternyata masih belum bisa ditinggal gitu. Jadi ya mohon maaf untuk itu ya. Sebetulnya saya sendiri juga sangat ingin sebetulnya ya bisa ketemu langsung gitu setelah sekian lama ya ngajar online itu juga kurang nyaman begitu. Jadi sebetulnya sudah sangat ingin begitu ya bertemu offline, tapi ya harus bersabar dulu ya. Mudah-mudahan ya kita berdoa aja semoga pekan depan tidak ada halangan, jadi kita sudah bisa bertemu secara offline begitu ya. Mudah-mudahan semua yang di sini dalam keadaan sehat ya. Ya, dan saya yakin ini pasti semua sudah di Surabaya ya, jadi sebetulnya sudah di Surabaya semua dan perkuliahan yang lain juga sudah berjalan. Ya, tapi nggak apa-apa kita coba berusaha semaksimal mungkin ya dengan resources yang ada sekarang begitu. Baik, jadi kode untuk hari ini sudah dimasukkan semua ya. Baik, kalau sudah ini saya akan tutup. Ya, dan mungkin sebagian besar sudah ketemu saya sebelumnya ya. Karena memang saya ini ngajarnya lumayan bervariatif ya. Mungkin dari yang semester 2 ada yang dipegang algoritma pemrograman, kemudian Makflu 1, Makflu 2 ya, kemudian apa lagi? Analisa numerik ya, sekarang MKE. Jadi memang apa yang saya ajar banyak mata kuliah basic ya, dan sebetulnya saya senang ajar mata kuliah basic supaya bisa tidak hanya transfer ilmu ya, tapi ada proses mendidik di situ gitu ya. Dan ya alhamdulillah sebagian besar sudah familiar ya, sudah familiar dengan saya. Mungkin sebagian besar juga di kelas Y sebelumnya ya di analisa numerik begitu. Ya, jadi karena ini kelas berbahasa Inggris ya mungkin sebagian sudah kenal. Jadi kita udah nggak perlu perkenalan lagi ya rasanya. Baik, nah mungkin mata kuliah yang baru ini adalah MKE ya, mesin konversi energi, di mana ini kelas Y. Jadi nanti kita akan menggunakan bahasa Inggris juga ya di dalam perkuliahan, dan nanti saya harapkan semua juga bisa praktis ya dalam bahasa Inggris. Jadi saya akan berbahasa Inggris, Anda pun juga akan berbahasa Inggris begitu ya. Jadi dalam diskusinya. Tetapi seandainya memang ada kesulitan, tidak tertutup kemungkinan juga untuk bisa dalam bahasa Indonesia ya. Tapi kita memanfaatkan fasilitas kelas Y ini untuk sekaligus berlatih bahasa Inggris ya. Nah kemudian ya alhamdulillah ya walaupun secara online sudah bisa melihat wajah-wajahnya di sini. Baik, coba saya mungkin coba kita ini ya lihat sedikit materi kita tentang MKE. Jadi MKE ini sudah dipelajari sebelumnya sebetulnya ya dalam bentuk mata kuliah yang terpisah-pisah ya. Jadi apa yang akan kita pelajari di MKE itu sebetulnya merupakan summary ya, summary dari yang sudah kita pelajari sebelumnya, mungkin di thermodynamics ya, kemudian mungkin di fluid mechanics juga. Jadi apa istilahnya di sini sesuatu yang lebih applied ya. Jadi mungkin lebih banyak apa mereview apa yang sudah dipelajari sebelumnya begitu ya, mereview apa yang sudah dipelajari sebelumnya dan melihat aplikasinya secara real. Bagaimana peralatan itu atau perangkat itu digunakan di dalam industri ya. Jadi artinya sesuatu yang kita pelajari nanti bukan sesuatu yang baru ya, bukan sesuatu yang baru. Hampir semua sudah dipelajari sebelumnya seperti itu. Jadi lebih banyak review dan lebih banyak discussion ya. Nanti harapannya di mendekati akhir perkuliahannya, jadi setelah midterm exam, setelah ETS nanti kita ada presentasi. Jadi nanti akan dibuat grup ya, akan dibuat grup dan nanti saya yang akan membagi grupnya begitu ya, akan membagi grupnya supaya acak begitu ya, sudah supaya tidak ada preference terhadap anggota kelompoknya sendiri begitu ya. Jadi nanti saya akan acak, kita buat acak aja. Nah, nanti akan dibagi 9 kelompok ya. Akan dibagi 9 kelompok. Nah, setiap kelompok nanti akan presentasi. Jadi kita mungkin akan menghabiskan sekitar 3 pekan ya, 3 pekan terakhir yaitu mulai pekan ke 13, 14, 15 itu adalah untuk presentasi. Nah, nanti materinya adalah nanti kita sampaikan ya. Nanti ini di sini nanti kita akan lihat nanti setiap kelompok akan punya topik ya. Akan punya topik dan nanti akan presenting begitu. Jadi kalau kita ada 30 dibagi 9 ya. Jadi sekitar 3 atau 4 ya, mungkin seperti itu. Ada yang 3, mungkin sebagian besar 3 orang, nah nanti presenting seperti itu. Dan presentingnya nanti in English ya, dalam bahasa Inggris. Nah seperti itu. Oke, jadi karena ini memang materi yang sudah banyak dibahas sebelumnya, jadi kita banyak discussion. Ya, ini coba saya share screen. Oke, dan ini kelas C ya, jadi kita akan pakai bahasa Inggris. Ya. So about this course, what we are going to learn is that we're going to learn about energy conversion system, yeah, in which we have learned most of that in thermodynamics, fluid mechanics, yeah, and we will see that we can apply that in actual cases, in real problem, yeah. Okay, so the credit for this course is 3 credits of study. So it means that we will need 50 times 3. So that will be a total of 150 minutes. So that will about 2.5 hour. Yeah. And the prerequisite is thermodynamic and fluid mechanics. And you're in the 6th semester. So I think there will be no problem at all. Yeah. You have taken all of those courses needed. And this is me. And for the component for the marking, yeah, as usual in my class, we will have 5% of class activities, yeah. So it means that I will record your activity during the class because we will have lots of discussion in this course. So that means I will record your activity, yeah. And also we will have assignments, yeah, and presentations. So this will be after the midterm exam. And we have quiz, midterm exam and final exam. And usually for the midterm exam and final exam, we have parallel classes so that we will have the same problem sheet for the midterm exam and the final exam. Yeah. So this is for the marking components, and this is not very strict. It means that I can change the percentage for the marking. So that's to make sure that most of you can pass this class and could have a good mark on this course. Yeah. But in general, this will be the components, yeah, the components for the marking. Okay, so this is the rules in the class, and I'm hoping that we will have offline classes starting next week, yeah. So please stop me when you do not understand, yeah, particularly because we are speaking in English, so that if you find it difficult to understand or if I'm speaking too fast, so that you can stop me, yeah. And you can ask me when you have questions. And I really hope that this class will be interactive. I want you to speak up and discuss. Yeah. And please drop the class if your mid evaluation is E. Yeah, so that if you have a midterm exam and then your result is E, I think it will be very difficult for you to pass this class. So that it's better to drop the class. Yeah, if the mid evaluation is E. And please no taking photographs. Please make notes. Yeah. And this is particularly if we have the offline class. Yeah. So if we have the offline class, usually happens a lot. You just taking photograph of what I've written on the whiteboard. But instead of that, I want you to take notes of what I have written on the board. Yeah. Okay. So that will be the rules, and we have agreed on that. Yeah. Okay, for the reference book, so I will show you here, we have a reference book which is written. Yeah, so this book, can you see this? So not sure you can see this. Okay, so I will take photographs of it later. Yeah, or I can, yeah. So I'll take a photograph of it and I'll send it in the group. Yeah, on the WhatsApp group. And yeah, about the WhatsApp group, if any of you have not joined the WhatsApp group, you can join the WhatsApp group. Yeah, so has everybody joined the WhatsApp group already? Semua sudah masuk dalam WhatsApp group ya?
Oke, ma'am.
Oke, karena saya lihat WhatsApp grupnya hanya 27 ya, 27 mungkin yang ada di WhatsApp grup. Sementara di sini saya kurang tahu ada berapa ya. Ada 30 ya. Jadi mungkin ada beberapa yang belum masuk, nanti bisa masuk di grup ya. Nah, ini coba saya okay, so we will see here that I will take photograph of the book and yeah, so that you can find the book. So this is a printout book. We don't have the soft copy of it. And this is written by the late of Mr. Astu Pujanarsa and Professor Jati Nur Suhud. So both of the authors were the lecturer in mechanical engineering department. Ya, jadi ini dulunya keduanya ini adalah beliau berdua ini adalah dosen di teknik mesin, ya, tapi keduanya sudah meninggal dunia, tapi sudah membuat buku ya, mesin konversi energi, dan kita tetap akan menggunakan buku itu. Jadi ini penerbitnya dari Andi. Dan ini bisa dicari di mana-mana. Terakhir di Togamas masih ada ya, seperti itu. Bisa dicari di Togamas atau di toko buku yang lain. Ya. If you cannot find this book or you don't want to buy it, so you can borrow it from your senior. Ya. Okay. So this will be the book that we use. And we also have supporting books. Yeah. So the supporting books is the power plant technology. This is quite an old book written by El Wakil. And energy conversion by Goswami Keith. Yeah. And also energy conversion by Kenneth Weston. Yeah. So that will be, those will be the book that we use throughout this course. And I will also supply the lecture notes in the form of the slides. Yeah, so I will supply the slides to you. And all of the slides, we still use Classroom, so that all of the slides will be uploaded through Classroom. Yeah, so that I will upload it there so that you can download the slides. Yeah. And the slide might contain combination or compilation from all of the book there. Yeah. Right. So this is the book. And when we talk energy conversion, so yeah, we will learn about the energy conversion system and what is the learning outcome for this course is that you are expected to able to understand and able to analyze the energy conversion system of conventional and non-conventional system, so that we will learn later that we have a conventional, which is already developed years and years, many years ago, and we have non-conventional system in which this is quite new, and non-conventional system is usually related to renewable energy. So we will learn about that as well. Yeah. And also here, it is expected that you will be able to perform calculation of basic characteristics and performance of energy conversion engines. Yeah. So I think this will not be difficult if you have a good basic on thermodynamics and also fluid mechanics. Yeah. Because when you have the good understanding on that, so this will be very easy. So most of the time, the student can pass the energy conversion course very good. Yeah, so usually the passing grade is quite high. Yeah, so that this is not a difficult course. So that what will be covered in this course. So we will have an introduction, which is discussed today. Yeah, and we will talk about conventional system. Yeah, conventional system, which this will cover what you have learned in thermodynamics. So I think you have learned about internal combustion engine before, and the second thermodynamics, yeah, in which you learn about gasoline engine, you learn about diesel engine, and you learn about gas turbine engine. And when you remember on this one, yeah, when you do review on this one, so you might relate this system, yeah, the process or the cycle in this system, you can imagine that in, for example, in PT diagram or PV diagram, yeah, and the PV or TV diagram, yeah. So when you remember of this, yeah, so that you remember the cycle as well, yeah, how the processes in the cycle. So this will be covered. So you will see that there will be a little bit of overlap, yeah, a little bit of overlap between thermodynamics and energy conversion system. And also we will talk about external combustion engine, which is this is relates to steam generator. And you have learned about this as well in the first and second thermodynamics. Yeah. So you see here that this is nothing new. Yeah. In terms of the cycle, in terms of the processes, you already learned about that. But we will see more in the application. Yeah. And we also learned about turbo machine, so that we will talk about steam turbine, which is used in the power plant as well, and water turbine, usually in hydro power plant, yeah, and also pump and compressor. Yeah, so we will learn a bit about that. We learn about how is the characteristic, the performance characteristic, and how is the application, what is the effect of the changes in the operations. Yeah, so we learn about that, which is more relates to the applications and what sort of problem that may arise in the operations. So this might be very useful for you later when you learn on this sort of plant which utilize these equipments. Yeah. And also we will learn a bit about refrigeration and air conditioning system. Yeah. So you've learned about this as well in the second thermodynamics. So you see here that there is nothing new. Yeah. So we do lots of review here, and we see how we can apply that in the real plant. Yeah. And also we will talk about non-conventional energy conversion, and this is relates to renewable energy. Yeah, so more advanced energy system in which we can talk about water turbine. Yeah, so this is also relates to hydro power plant. Now we have micro hydro as well. Yeah, for small scale, uh, uh, small capacity, and also we have wind turbine, geothermal, solar thermal, OTEC. Any one of you heard of OTEC before?
Yes, ma'am. Yes, I did.
Yeah, what is that? What is stand for?
Using surface temperature of seawater and for heating the refrigerant.
Yeah.
And refrigerant is for spinning the turbine.
Yes, correct. Yeah, so utilizing the difference of the temperature on different depth, yeah, in the seawater. Yeah, OTEC. connected. So we will return on the slide, yeah. Right. So here, these are the topics that we will discuss for the presentation. Yeah. So that we will have 9 groups, and each group will receive a topic to be presented. So that I will share the groups later. Yeah, probably next week or the week. Okay, right. Yeah, you can hear me now? Yeah, sorry. Yeah, it looks like the problem with the computer. It becomes too hot, so I have to find fan first, yeah, to make it cooler. All right. All right. So these are the topics, yeah. So that we will have groups for that, and we will discuss on that later. Yeah. All right. Now, before we talk about energy conversion, so we have to see that we have classification of energy, yeah. So that we have the terms of transitional energy and we have the term of stored energy. So stored energy is the energy content of a mass, yeah. So that the stored energy, for example, we have the energy in coal, yeah, or fuel. So that is a stored energy. But also we can have a transitional energy in which this is transferred across the boundary or converted into useful energy. So the example is heat and electricity. So this is just a classification of the energy. And if we look at the form of energy, yeah, we can have the internal energy. I think we have learned about that before in thermodynamics as well. And we have chemical energy, yeah, in terms of chemical substances. We have electromagnetic, we have nuclear, and mechanical. Yeah. So this is the most common that use, which is a mechanical energy. So this is dealing with, for example, rotation of the shaft. Yeah. So those are mechanical energy. Or for example, we have a translation in the piston head. Yeah. So this is mechanical energy as well. So this is dealing with movement. Yeah. And for the energy sources, we can have the terms of terrestrial or extraterrestrial. Yeah. So when we talk about terrestrial, is something that is comes from the earth. Yeah. While extraterrestrial is something that is beyond the earth. Yeah. Something in a larger area. Yeah, which is extraterrestrial, outside the earth. So this is just a classification of the energy. So that when we talk about energy conversion, in which we learn here the system of converting the energy, so that we have several form of energy. For example, we have the mechanical energy, we have electrical, chemical, radiant, and thermal here. So then we can have a change, yeah, of the form of the energy. For example, yeah, from mechanical into thermal, in which this is occurring in friction, yeah, or we can also in the reverse direction, which is thermal to mechanical, in which this is in the form of the engines, yeah, and so on. So we can transform the energy form, yeah, the energy form, and of course the process here has a direction, yeah, as well. There is a governing to the direction of the process, yeah, in which we have learned in the first thermodynamics, yeah. So this is relates to the entropy as well, yeah, in which this would govern the direction of the process. But yeah, But with this form of energy, we can make a system, or we can arrange do manipulation to change the form of the energy. And this is what we do in the energy conversion system. So if we look at the energy sources, we have non-renewable or renewable. And for the non-renewable, we have terrestrial or depleted energy. So the terrestrial is something from Earth. Here we can have fossil fuel in terms of coal or liquid fuel or gas, for example. So those are fossil fuel. And also we have nuclear. So this is also terrestrial. So this should be terrestrial, And also for the renewable energy or non-depleted energy, here we have terrestrial and extraterrestrial. So extra here is, for example, the solar energy, So this is the energy from the radiation from the sun, So solar energy here is included in extraterrestrial. Well, what is included in terrestrial is biomass, So now it's being developed. It is biomass. And so this is a fuel which is come from the excess we can use that from wood chip and so on. We have also biogas, water, wind, and geothermal. So the water itself here can be in the form of hydropower, or in the form of sea or ocean, ocean energy, for example, wave, tidal, and ocean thermal. So these are the example of the energy sources in which we will discuss about that and how to convert this useful energy into electricity. So mainly into electricity, or also into torque or power to drive an engine, for example. So then when we talk about the engine itself, we have two types of engine. We have the heat engine and we have the cold engine. So when we talk about heat engine, this is something more related to thermodynamics. When we talk about cold engines, so this is more related to fluid mechanics, or turbo machineries. So that we see here, we have heat engine, we have internal and external, as we seen before. We will discuss all of that. Internal combustion engine includes gasoline engine, diesel engine, and Wankel engine. While for the external, we have steam turbine or steam engine. Now, anyone heard about Wankel engine before? We have Wankel engine. Yeah, you've heard about that before. Yeah. So what is that?
In my understanding, ma'am, Wankel engine is a gasoline engine, but instead of using pistons, they use a triangular shape piston, ma'am.
Yes. Yeah, correct. So the shape of the combustion chamber is different. So it's using a rotary system. So that is correct. So, but basically it's similar. So the other to the piston engine, but the shape is different. So the shape is different. So this is called Wankel engine. So usually this is used in where? Do you know that?
Used in car at X7.
Yeah, okay, in Mazda, okay. So that is Wankel engine. So we will look at that a bit, So this is what we are going to learn, aside from heat engine, also cold engine. And we will learn about this in terms of the performance, So what you have learned in thermodynamics is more on the basic, on the fundamental, in which you talk about the diagram, you talk about also you talk about efficiency, but what we see here is more in applied. So when we talk about efficiency, so we talk about something which is the total efficiency, the total efficiency of an engine. All right. And we're also going to learn about external combustion engine, which is used in power plant. We have steam turbine and also we have steam engines. And also relates to that, you should remember that when we learn about steam power plant, so that we will talk about cycle, which is called what is is that? For the steam power plant, what cycle which is used?
Rankine cycle.
Rankine cycle. Yeah, Rankine cycle. Yeah, for gas turbine, this should include gas turbine as well. Yeah, gas turbine. So gas turbine is based on what cycle?
Brayton, ma'am.
Brayton cycle. Yeah, so that is correct. So when you talk about cycles, so you can imagine the diagram. Yeah, the diagram. All right. So this is we are going to talk about this one as well, and also for the power plant, we will discuss about the Rankine cycle, aside from the Rankine cycle, also the combined cycle. Yeah. So the combined cycle, we will learn about a bit about combined cycle as well. And I think you have learned that in thermodynamics as well. What is combined cycle? You still remember?
Like in PLTGU, ma'am.
Yes, correct. Yeah. So combined cycle means combination. Yeah, combination of the gas turbine and the steam power plant. Yeah, the steam turbine. So that we have a combination of the two. We have Brayton cycle and we have Rankine cycle as well. Yeah. So I think you have learned about that before. Yeah. And also called engines here, we have water turbines and wind turbines. So we will learn a bit of the basic theory, but not deep into that, because if you want to learn about turbo machinery in a deeper level, you can take an elective course of incompressible fluid machineries with Pak Herman. Yeah, but what we discuss here is only in general, and we will look at the performance. Yeah, so later, for example, when you work, yeah, and you came across with, for example, pump, or you have a turbine, yeah, so you understand the performance and the characteristic of those machines. Yeah. All right. So because what we've seen here is most of that has been learned before, so we will do a review. Yeah, so we will use today as a review to what we have learned before. Yeah, so this is to make sure that we have the same understanding on this, so that we can continue through this course easily. Yeah. Okay, so we will have discussion on this. Okay, the first one is the first law of thermodynamics. What is that? I think this is very easy. Yeah, the first law of thermodynamics.
Q equal to work plus internal energy.
Yeah, delta Q, Q plus work, that will be equals to the internal energy. Yeah, or that is correct. Yeah, so that is the equations. So that you say that this will be, this is not working. Wait. All right, so that you say Q minus W, that will be equals to delta U. Yeah. Or, yeah, how can you say that? What is the physical interpretation of that? The first law of thermodynamics, what is the statement? What is the statement? The first law of thermodynamics, what is the statement?
Ma'am, I think the statement is that energy cannot be created nor it can be destroyed.
Yeah, correct. So it cannot be created. Yeah. So Anga was saying that cannot be created, cannot be destroyed, but it's only can change the form or transform. Yeah, it can be transferred and it can be transformed. Yeah, so that we have the transfer of energy in terms of Q, which is stated here. Q is the heat. Yeah, and we have W, which is the work. So this is a change of energy. So that if we have a change of energy, yeah, or delta E, yeah, so usually we have delta E, yeah, so delta E, the change of energy, so that will be delta EK plus delta EP, the potential energy plus delta U, yeah, so this is actually the delta energy. So yeah, if there is a change, it means if there is a change of energy in the system, so that means that should be caused by an energy transfer through the system. Yeah, all right. So this is the first law of thermodynamics. And this is used everywhere in thermodynamics, in fluid mechanics. Yeah, everything is based on first law of thermodynamics. Yeah, all right. So the second is the energy equilibrium for the closed system. Yeah, energy equilibrium for the closed system. I think we already have that before. Yeah, so this is the energy balance for a closed system. Next, reversible process. What is reversible process?
Oh, I think the reversible process is when the entropy is equal to 0, ma'am.
Correct. Yeah. So the entropy, or can you say more accurate? When we talk about process, so that we talk about the changes from the state, from state 1 to the second state. Yeah. So what? Yeah, almost correct. So when the entropy, yeah, or when the delta entropy, yeah, so the changes of entropy, yeah, the changes of entropy is equals to 0. Yeah, because we have the state here, we have the entropy for the first state and we have the entropy for the second state. So it's said to be reversible if there is no increase of entropy in the process. Or what is physically, the physical meaning of reversible process?
I think reversible process is when there is no.
Yes.
When there is no gesekan.
No friction. Yeah.
No friction, yes.
No friction. Yeah. Reversible process when there is no friction. Okay, so this is one of one of the causes, yeah, of the increase of entropy throughout the process. Yeah, but what is the physical meaning? So that is one example. Yeah, so that is correct. No friction. So that is one of the example. Yeah, but what is the physical meaning of reversible? So reverse mean returning back. Yeah, so reversible process means that the process can be returned in the same way. It can be performed from 1 to 2 or 2 to 3 using the same, exactly the same step. Yeah, exactly the same process. All right. So this is reversible. So this is correct. Yeah, for the definition of delta S is equal to 0. Now we have the constant volume or constant pressure processes. What these processes mean? Constant volume?
Constant volume when the water is not tetap, ma'am, waternya tetap.
Yeah. So when we have the volume is constant, yeah, when we have the volume is constant, or you can say we have a the analysis, yeah, the system that we analyze has a constant volume. Yeah, so constant volume. So that is correct. And we can draw that in PV diagram. Yeah, so if we have a PV diagram, so that the constant volume process, yeah, a constant volume process will be shown. Yeah, so if we have a PV diagram like this one, so the constant volume process will be shown with what line?
Vertical line, ma'am.
Yeah, correct. So that will be a vertical line. So this will be the constant volume. What is the other name for constant volume process?
Isochoric, ma'am.
Isochoric, yes, so that is correct. Isochoric process. What about constant pressure?
horizontal line and there is a work there.
Yeah, right. So when we have a constant pressure, yeah. So when we have a constant pressure, so that means we have the horizontal line, yeah. And what would you say after that?
And when is isobaric process, there is a work on that process because the volume is different.
Oh yeah, okay. So that is a work, yeah. So when we remember how we can calculate the work, so the work will be the integration of P dV, yeah, P dV, right? So then if we have a constant pressure, so it can be a work. While constant volume means that the volume is constant, so that we can say, yeah, so that, yeah, the work in this case can be 0, yeah, all right. Ideal gas. What is the definition of the ideal gas? All right. We often assume air, for example, we assume air as an ideal gas. So we commonly use this one. But what is actually the definition of ideal gas? And whether all of the substance gas substance can always be assumed to be ideal gas. Back again to thermodynamics. I think this is in the first thermodynamics.
Ma'am, maybe is assumed as ideal gas because CV and CP is almost constant. Whenever the temperature is changed, the CV and the CP is can be assumed constant because there is a little bit a change, but not huge change. So
Yeah.
it's a little bit different value.
Okay. So we have a parameter for that. Can you remember what is the parameter to define whether a gas can be classified into the ideal gas?
Maybe the K is 1.
K, is it? No, not yet. Not K. K, you said K, is it? K? Specific heat ratio, is it? Is it equals to 1? No. What parameter that is used to define whether the gas can be assumed to be an ideal gas? Back again in the first thermodynamics, I think it's in chapter 3, if I'm not mistaken. It's on the 3rd semester. Now you're in the 6th semester, so it's about 1.5 year ago, yeah. All right. What parameter? It's Z parameter, remember?
Big hit, ma'am, maybe.
Yes? Remember Z? We have that symbol Z, remember? Not yet, okay. So you can open the book again. So this is compressibility factor, yeah? So not K, but Z. Z here is the compressibility factor. So when we have the compressibility factor of 1, so this is equals to 1. So that means we can assume that to be an ideal gas, yeah? All right. Okay, so that is an ideal gas. And the equation for the calculation of the ideal gas. Now we're getting deeper on that, yeah? What is the equation for the calculation of an ideal gas for the isothermal process? Isothermal. So isothermal means that the temperature is constant, yeah? Or before that, yeah?
P over V equal to constant.
Who's answering? Can you repeat? Atim?
P over V is constant.
P over V is constant. Yeah. All right. We will look about that. Next, isobaric process. Isobaric. Isobaric process, it means that, yeah, the pressure, yeah, so baric is pressure. So this is constant pressure process, yeah. So that with the constant pressure process, what it means? So that for the ideal gas, basically we have PV equals to RT, yeah?
Or maybe V
yeah.
times T constant, ma'am.
V times T is equal to constant, okay? All right. Isobaric.
Isobaric P over T equal to constant.
P
over T.
P over T is constant. Yeah. All right. So we will just look at that. Later we will discuss about that. We will see. Adiabatic process or constant heat capacity.
Q equal to 0, man.
Q. Yeah. For adiabatic process, yeah, correct. We have Q is equal to 0. Yeah. Yeah, of course. Adiabatic process, Q is equal to 0. Yeah. But then we will see, yeah, that we can apply these processes into the calculation of ideal gas, so that this will be a task for you to look at again, yeah, to the thermodynamics book, that we have the calculation for the ideal gas, yeah. The basic equation is this one, so that you can apply the, yeah, we can apply the processes here, yeah, to obtain the calculation. Now we will look about that again in brief later, yeah. And we have also polytropic process. Now what is this polytropic process? Yeah, can you remember what is polytropic process?
P times V or N equal to constant.
PV N equals to constant. Yeah, so this is the definition of polytropic process. So it will follow this equation. Now we will see if this is this correct? P over V is C. It is P over V.
No, ma'am, it's not correct, ma'am.
Yeah, so what is the correct one?
P times V.
Yeah, so that should be
P times C.
Yeah, equals to constant. And this one?
P over T.
P over T.
P over T, constant. Okay. All right. Now this one is correct, yeah? All right. So then next we have the first law of thermodynamics for the open system. Now this one for the closed system, yeah? And now we have the open system. So how to write down the first law of thermodynamics for the open system? So that when we talk about open system, so there will be a change of time, yeah? Because we talk about mass flow rate then, yeah. What is the first law of thermodynamics for open system?
U dot minus work equal to d dt del t integral rho del v. Pokoknya yang ini, yang transient, mem, terus ditambah m dot rho dv plus m dot dalam kurung enthalpy plus V kuadrat per 2 plus GZ.
All right. Yeah. It's sort of mixed up between the equation that you have in fluid mechanics and the equation that you have in thermodynamics. Yeah. All right.
Yes, ma'am.
All right. Who can fix this? Who can fix this? This sort of mix up. Yeah. Actually, this is the same. Yeah. So if you have the equation of thermodynamics in fluid mechanics and also in thermodynamics, it will be similar, but we have a different convention of how to writing it. Yeah. All right. Yeah. In general, this is correct. Yeah. Usually usually we do this one. Yeah. In thermodynamics. Yeah. All right. And then we have irreversible process. Yeah, so this will be the opposite of reversible process, in which in irreversible, it means that it cannot return to the initial state, yeah, using the same process, yeah, irreversible. And as again, we see that delta S will not be equals to 0, yeah, because there always an increase, yeah, there always an increase in entropy. Now, when we talk about entropy, so what is actually the meaning of entropy? What is the definition of an entropy? All right, who can answer that? We have talked about internal energy. I think everybody is already clear about internal energy. This is an energy content, yeah, energy content of a substance, which is internal energy. So that will be useful. Yeah. We have kinetic energy, that is clear. We have potential energy, that is clear as well. And we have enthalpy. Yeah, we have enthalpy and entropy. So what is enthalpy? Review. What is enthalpy? We just stated here H. Yeah.
U plus PV maybe.
Yeah, that is correct. Yeah, so enthalpy is internal energy plus PV. So we have the pressure, yeah, more energy in terms of pressure and specific volume. Yeah. Now, what is entropy then? So this is dealing with S or entropy. So what is actually entropy?
Maybe entropy is the measure of randomness or disorder, ma'am.
Okay, correct. So this is a measure of randomness or disorder. So it means that entropy is an energy as well. Yeah, is an energy, but we cannot use that energy. Yeah, we cannot use energy. So when we have an increase of entropy, it means that the useful energy will be decreasing. Yeah, it means we have losses in there. Okay, so that is correct. Last, we have stagnation condition. Okay, so what is stagnation condition? Yeah, stagnation condition. Still remember stagnation point? We have stagnation point in fluid mechanics. What is stagnation condition?
Where the velocity equals to 0, ma'am.
Okay, yeah, correct. Oh, equals to 0. So velocity equals to 0. Any other? Is that all already? Or is there any requirement aside from the velocity 0? Is that complete already? Stagnation condition, the velocity is 0. Everybody agree with that? Or do we need to define more?
The separation of the streamline, ma'am.
The separation of the streamline. Is it? So we have stagnation point, we have separation point. So what you have talked about is about dealing with separation. Is it the same between stagnation and separation? No, it's not the same. Yeah, so it's different. So what is stagnation then? When we talk the velocity is zero, yeah, that is correct. In stagnation conditions, the velocity is zero. But for example, if we have a plate, yeah, we have a plate, and we know that there will be boundary layer here. So there is a no slip condition here. And the velocity will be zero here. Is this
Your voice, ma'am.
Yeah, sorry. Yeah, it looks like very challenging today. All right. Go back to our discussion about stagnation point. Yeah. So what is the difference between stagnation and separation? I think it's very different. Yeah. So what is the definition of stagnation?
Gak ada suara ya, Anjir? Oh, excuse me, ma'am. Excuse me, ma'am.
Yeah, can you hear me?
Yes, ma'am.
Okay.
Okay, ma'am. Sorry, ma'am. About the stagnation point, in my mind, stagnation is like when the flow at the point it was brought to the zero velocity in isentropic condition.
In isentropic condition. Yeah, so that is correct. Yeah. Yeah, so that is correct. So in isentropic condition, it means that there will be no losses. Yeah, during in which the velocity is when the particle of the fluid is stopped. Yeah, so that is correct. Yeah, so stagnation condition. So that dealing with stagnation condition, we have the terms of total energy. Yeah, so dealing with stagnation conditions, we have terms of total energy, usually in the form of the total pressure. Yeah, and also later when we learn about fluid machineries as well. Yeah, we also dealing with total temperature. Yeah, total temperature. Yeah. So when we talk about total pressure, actually this is a stagnation pressure. Yeah, so this is a stagnation pressure, or we can call that as the total pressure. So remember what is the total pressure or stagnation pressure? So this is in second fluid mechanics. We usually denote that with P0. So P0 will be equals to the total pressure or the stagnation pressure, that will be equals to
pressure head and velocity head.
pressure head and velocity. Yeah, or we can head is usually in different head is in different units. Yeah, head is different unit to pressure. So in pressure, here we use the term pressure, so that will be the total pressure, that will be equals to, yeah, that is almost correct, but not head. So that will be almost correct. Yeah, wait for a while, yeah. Yeah, so total pressure, so that will be equals to almost correct. Yeah, almost correct. What is total pressure? Yes.
Maybe P atmosphere and plus P fluid. Yeah.
P atmosphere plus P fluid.
Yes.
Pressure, the pressure of the atmosphere plus the pressure of the fluid. What do you think? So Masayu was saying that. How can I call you, Masayu or Anggita?
You can call me Masayu or Mir.
Oh, Mir. Okay. Okay.
Ma'am, I think it is static pressure and dynamic pressure.
Okay. Yeah. So that is correct. Yeah. Static pressure plus dynamic pressure. So what is the dynamic pressure?
Rho P quadrat.
Yes. Can you repeat, Sultan?
1/2 times density times velocity power of 2.
Yeah, okay, so that is correct. Yeah, so the total pressure or the stagnation pressure is the addition of the static pressure and the dynamic pressure. So this will be the dynamic pressure. Dynamic pressure. Okay. So another question: what is this? The one that is answered by Masayu, yeah, or Mir, yeah. What is this?
Absolute pressure, maybe.
So this will be the absolute pressure. So that is correct. Yeah. So this is absolute pressure. And this one will be, when we talk about this one, so this will be
Gauge pressure.
correct. So this will be the gauge pressure. Yeah. So that is correct. Now the question is when we have this one, yeah. So that what is the pressure that is used in thermodynamic stable? When we have thermodynamic stable, we have to find the properties. Yeah, usually we need two properties to define the state, yeah, or the condition. So which pressure is used to find that in the thermodynamic stable?
Absolute pressure.
Yeah, so that is correct. So that will be absolute pressure. Now the question is which one? Is it the total pressure or the static pressure? Which one? Which one?
Excuse me, ma'am.
Yes.
I prefer to adim, but with plus gravitational potential energy per volt. I thought.
Which one? This one?
Oh, adim one.
Okay, so the total pressure, yeah. All right. So you will add the total pressure with gravitational.
Yes, ma'am.
All right, yeah. All right, we will discuss again about that later, yeah. All right, so we will continue this first, yeah. So you can check again in the book, yeah. All right. Yeah, all right. So yeah, so this is already correct, yeah. So this is already correct. Yeah. When we talk about head, yeah, that is correct. When we talk about head later, we have gravitational included there because head means that that will be the total energy, yeah. But when we talk about pressure, so that will be composed of static and dynamic pressure, yeah. All right. Next, we have moment of momentum equations. Remember of this one? So this is in fluid mechanics. moment of momentum. Yeah, it's still a year ago. This is on the first semester. Yeah. Okay. So I doubt that you remember. So we will look on the explanation. Yeah, we will look at the explanation. So yeah, when we talk about processes, so that we will back again to use PV and DV diagram in the analysis. Yeah. So this is just to remind you what you have learned. Yeah. In thermodynamics. Yeah, so we will utilize this one, especially this one in Rankine cycle. So we will look at this dome, the area, the mixture between liquid and vapor. And then we also going to play with this diagram as well. Yeah, it's not as very detailed as what you have learned in thermodynamics, but we will do similar calculation to that. Yeah, and also here we have an isobaric line. The isobaric line is the constant pressure line. So here we have the isobaric line. When what is the isothermal line? So that will be the horizontal line here. Yeah. And also we have the PV diagram here is also shown here, so that we have these lines will be the isothermal line. So I think you have already understand about that before. So this is just a review. And also we can have entropy. We can find that as the TS diagram or HS diagram. So entropy diagram. And here we have the blue shaded area here. This is the area of the ideal gas. So when we talk about the ideal gas, so that we will not have the dome here, but we talk about the area on the right side of the dome here. Yeah. Okay, so this is quite similar to TV diagram, but it says the shape of the dome is slightly different. And here we have S, yeah, as an abscess. Okay, so I think you already learned about this as well. And also we have, the enthalpy entropy, or this is called the Mollier diagram. And we have also the pH diagram, yeah, the pressure enthalpy diagram, particularly when we talk about refrigeration system, yeah, later. All right, so this is the critical point. Remember what is the critical point is?
It's a point that where the phase is will be changed, man. From liquid into the vapor.
So
it's like a critical temperature.
Yeah, so in the critical point, we have critical temperature and we have the critical pressure as well. Yeah, so what is the critical point? When we have a phase change, so then, at this point, beyond this point, it means that we will not have a phase change between liquid and vapor. Yeah, so beyond this point, so up of this point, we don't have a phase change. Yeah, so the phase will be the same. Yeah. Right. So this is reversible and irreversible process, so that I think all of you already understand. We have discussed about that, and this is correct already. Yeah. So when we have reversible, it means that delta S is equals to 0, or when this equals to 0, and or we can say that the entropy production is 0. Yeah, the entropy production is 0. Okay, so this is just a review of what we have learned in thermodynamics. Yeah. And about polytropic process that we have discussed before, so that is correct. Yeah. So polytropic process means we have a correlation of P times V to the power of N is constant. Yeah. And looking at this, when we talk about isobaric process, isochoric process, or isothermal process, when we have an ideal gas, yeah, so that we have here, say we have N here is 0, so that will be P constant, yeah, so that will be isobaric. When N is approximately infinity, so this means that the volumes becomes more dominant compared to the pressure, or that we can say that the volume will be equals to constant, or we can say that we have an isometric or isochoric process. And if we have an ideal gas, yeah, when N is 1, so that we will have the constant temperature or isothermal process. So we have discussed before, if you have isothermal, so that will be P times V equals to constant. And if we have N equals 2K, yeah, and equals to k. So it means that we have a correlation of p phi to the power of k that will be equal to constant. So that means we have adiabatic process in which there will be no heat transfer, or Q is 0. Yeah, so if we have Q is 0, so that this imposes that N here will be equals to K, or the specific heat ratio of the gas. Yeah. So this is a review. Yeah, again, dealing with the work done. I think we have discussed about that before. Yeah, in which we can apply the processes into the calculation for the work here, so that we can find the work. Yeah, so this is just a review of what you have learned before. And what if we have the ideal gas? Yeah. So if we have the ideal gas, so this is the basic equations, the equation of state for the ideal gas, so that we can change that if we have the polytropic process. Yeah. So if we have a polytropic process as this one, so that we can find the work for each of the processes there. And the moment of momentum equations. Now this is the equation shown here. And I hope you still remember this. Yeah. So moment of momentum here is used in fluid machines. Yeah. What we have learned in fluid mechanics is that the example is sprinkler. Yeah. So that what is the moment of momentum? So here we have the torque, and the torque here is in the form of the surface force times the length, yeah, or the radius to the center of the rotation, plus the weight, yeah. So this is the weight times the radius plus the torque of the shaft. So that will be equals to del over del T integration controls volume R cross phi rho dV plus the integration of control surface R cross phi rho phi dA. And this is the first law of thermodynamics in fluid mechanics. Yeah, so we have seen this in control volume analysis before. Yeah, so this is what we have learned before, and this is just a review. Yeah, of what you have learned. Yeah, so that we will apply that in a more practical way. Okay, so back again here, when we have the definition of renewable and non-renewable, so that again, yeah, when we talk about renewable, it means that it's easy to be regenerated, yeah, in a relatively short period of time. While non-renewable is take very long time, or we can say that it cannot be replaced in a short amount of time. Now the question is, what about, yeah, so I think it's already clear, yeah, non-renewable is fossil fuel, yeah, nuclear, it's not a non-renewable. For the renewable, we have water, we have a solar, yeah, we have wind. Now, what about geothermal? What do you think of geothermal? So it's geothermal is taken from the earth as well, yeah. So it's taken from the inner of the earth, utilizing the heat from the earth. What do you think of geothermal? Is it renewable or non-renewable?
I think it's renewable, because as long as the earth is alive, the heat from the earth can be used for the power plant. Okay. I think like that, ma'am.
All right. Yeah. Yeah. So yeah. Yeah, for geothermal, it's utilizing the heat from the earth. Yeah, of course, when we do, we create a well, yeah, to absorb the steam from the earth. Yeah, in the term of geothermal, of course, we take the steam out of from the core of the earth. Yeah, so that steam is taken, yeah, and of course the sources of the steam underneath will be depleted, yeah, but then because we have rainfall and so on, so that the steam, yeah, can be generated quite in a short time. So usually it's included in renewable, yeah, so generally it's included in renewable sources, yeah, because the steam is can be regenerated in quite a relatively short period. Yeah. All right. So that is correct. So what is included in fossil fuel? We have coal, oil, and gas. Yeah, natural gas about 20% of world consumption of energy. We have gas power station. Yeah, so this is just a knowledge. Yeah, and fossil fuel are not renewable energy resource. Yeah, and this is the illustration of the energy sources. So say we have the oil well here, and we have the gas well, and yeah, it can be offshore or onshore. Yeah, it can be offshore here or onshore. And also we have coal, yeah, coal mine here, and we have geothermal here. So you can see that this is all actually exploitation to the earth. Yeah, so actually anything that taken energy from the earth, yeah, is actually an exploitation. So that we have to be very wise in using it. So we see here that the gas, oil, yeah, and coal here are taken from different layer of the earth. Yeah, so we can see here that we have a hard rock magma, or this is the core of the earth, and then we have some area which is close to the magma here, in which we have a layer of water, natural gas, yeah, and oil here. Yeah, so above the water here we have oil, and then we have the natural gas. So we can see that this is located at different depth. Yeah, different depth. Yeah, so we have oil here, we have oil well offshore and onshore. So this is taken at this layer, and a bit on top of it we have the natural gas layer. So here we have a gas well. So this is the well is drilled up to this depth. Yeah, and then we can take that natural gas. And for the geothermal, we can see here that this is a slightly higher layer here. So this is taken from the area close to the hot rock or the magma here, in which this is the water which penetrates to the uh, to the earth, yeah, going down through close to the magma, yeah, so that we can make a well here for the steam. We make a well. And when we can take the steam, yeah, so the water is heated and brought out as dry steam or wet steam. Yeah, so there are two types of steam, in which this is called the dry steam or wet steam. Anyone heard about that before? Dry steam and wet steam. What is the difference? Dry steam and wet steam. So both are steam, yeah, steam, but we have dry steam and and wet steam. Yeah, what is the difference? Yeah, so when we talk about steam, you remember for example, in PV diagram or TV diagram, yeah? So what is the location of the steam there in PV or TV diagram?
Inside the tube, di luar kubang.
Yeah, so when we have, for example, like this one, yeah, the steam, when we talk about steam, so steam is, yeah, that already, so if we talk about the area here inside the dome, so this is a saturated area, saturated region here, in which this will undergo the phase change. So we have the quality, yeah, we have the quality of the steam, or that will be the fraction of the steam. Yeah, so when we have a sort of this sort of steam well here for the geothermal plant, so that we can have a steam which has a quality here, yeah, close to the liquid, saturated liquid, or we can also have more to the right, or even here, yeah, in the saturated zone. Yeah, so that in the superheated zone, so that if we have a dry steam, so it means that we have this area, yeah, and when we have a wet steam, it's have a liquid content inside, yeah, so that this will be different, depends on on the nature itself. Yeah. So in Indonesia, most of the geothermal plant is wet steam. Yeah, utilizing wet steam. So has a water content inside. Yeah. Okay, so how is the treatment for that? How is the system built for the geothermal plant? So that will be depends on what is available here. Yeah, so that we will learn later that this geothermal plant will have different component as well. Yeah, different component for in which that extracting the dry steam or whether the extracted one is the wet steam. Yeah, so the cycle will be slightly different. Yeah, the equipment will be slightly different. Yeah, so that depends on the nature. Okay, so this is the example of energy sources. And then aside from that, what we have learned, yeah, so this is a mixture of everything that we have learned. We also learned about two-stroke engine and four-stroke engine. I think you have learned about this as well, yeah, in thermodynamics, is it? Or
Yes,
not?
ma'am.
Yes, ma'am.
Yeah, so you have to learn about that. So what is the difference between two-stroke and four-stroke engine? Two-stroke and four-stroke engine. What is the difference?
Maybe for the first stroke, there is four-step intake, compress, work, and exhaust. But for two-stroke, the intake and compress happen in the same time, and the work and exhaust happen at the same time too.
Yeah, so that is correct. Yeah, so for two-stroke engine, it means that we have two processes in one stroke. Yeah, in one stroke. So one movement will include two processes. Yeah, so that we have here. For example, here we have a power process. So this is going down. Yeah. So when we have a power process, so this head of a piston goes down, and when it goes down, then closer to the bottom end here, so that there will be an exhaust process because the port here is automatically open when it moves down. So that means we have a power and exhaust, two processes in one stroke. And then we have next the compression again as the intake. Yeah, when it moves to the top end, and then the intake port is open so that it's also taking the air and also the fuel in. Yeah. So yeah, we see here that we have two processes in one stroke. Yeah. In general, the cycle will be the same, but in mechanical side here, we see that this will be performed in only two strokes. It means that with only one revolution, we have the full cycle. Yeah, the full cycle in one revolution here. While for the four-stroke engine, this is correct before, yeah, which is said, yeah, four-stroke means that each step or each stroke here is performed only for one process. So that means if we want to perform the complete cycle, four processes in a cycle, so it means that we need two revolution. Yeah, we need two revolution to get the complete cycle. So that I think you have learned about this before, yeah, and you can imagine how is the PV diagram. So what we will see next later, what we will learn later in this course is that how is the performance? What is the difference of the performance between the two-stroke compared to the four-stroke engine? Yeah. One might say that two-stroke engine will have more acceleration, more torque. Is it correct? Yeah. What about the temperature? Yeah. What about the efficiency? So that what we are going to learn in this course. Yeah. So the basic theory is already thermodynamics, but what we will see here is more in applied. Yeah. What more in the performance characteristic. Right. So this is steam power plant as well. You have learned about this. Yeah. Yeah, we have learned about this before. We will take a break for a couple of minutes. Yeah, about 2 minutes. Wait a moment. All right. Okay, so yeah, back again. Here we have a steam power plant, yeah, in which I think we already know the components, yeah. We have learned about thermodynamics before. We have 4 main components of the Rankine cycle. What are the components?
Boiler,
Yes.
turbine, condenser, and pump.
Yeah, correct. So we have a pump here. Yeah, we have the condenser. Yeah, so this will be the condenser. We have the turbine. Yeah, so this is a first stage of turbine, and we have the boiler. Yeah, and we have the feed pump here. So this is the boiler feed pump. Yeah, the water feed pump. Yeah. Yeah, so that we have a boiler, turbine, condenser, and pump. So that is correct. So those are 4 main components that is used in the Rankine cycle. Yeah, but you have learned as well in the second thermodynamics that we can have many. In the first thermodynamics, we have many other components to support that. Yeah, for example, we can have the aerator, for example, yeah, and we can also have, for example, multi-stage. We can have economizer as well. So that is what we are going to learn as well. Yeah. Okay, so what happens here, if we look at the steam power plant, we have the chemical energy, yeah, and we have the heat here. So we have the fuel in the form of chemical energy here. So this is the internal energy, and this is heated, this is burned to create heat. So this heat is utilized to make steam, yeah, and after that the steam will be used to drive the turbine. So from heat here, there will be a change of energy form into mechanical, yeah, into mechanical. And after that, from mechanical, this is connected with the generator, so that becomes electricity, yeah. And this then connected to a grid, yeah, into transformer and so on, to supply the electricity, for example, to a city, yeah, or industry. Okay, so this is the energy conversion system. Yeah, so we can see there is a change of the form of energy, yeah, through heat or also through the work. And this is the example of the steam power plant, which is in yeah, quite simplification still, yeah, for the steam power plant. We have the coal here, which is fed into the conveyor, and then this will go into the crusher, yeah, into the coal bins, and then sent into the pulverizer or crusher, and then this will goes into the boiler. Yeah, so we have the boiler here in which the coal is burned, yeah, with the air. Usually we have 2 supply of air, yeah. So the air here is heated before it goes into the boiler. So we have air preheater here, and then this will be supplied through 2 ports. So usually we have the primary air and we have the secondary air, yeah. So we have primary and secondary. Usually primary will bring on the coal, while the secondary will be located, will be supplied to the sides of the boiler here, yeah, to ensure that this is burned efficiently, yeah. So this is burned efficiently. So yeah, and then afterward, the exhaust gas will be released to the stack, and the steam, the heat here will be used to heat the water into steam. So later we will look at how the boiler looks like. Yeah, so we have a water wall inside, and then we have the many shapes of heat exchanger. Yeah, for the boiler, for the evaporator, for the superheater and economizer and so on. Yeah, so from the boiler and superheater, then it brings the high pressure steam into the turbine here. Yeah, and the turbine will be connected to the electric generator. Yeah, and this will producing electricity to the grid. And from the turbine here, then the steam will be condensed, yeah, in the condenser. Yeah, and afterward it will be recirculated back here using the boiler feed pump. Yeah, boiler feed pump here. So it will be recirculated. And when we look about the condenser as well, so this needs to be cooled. Yeah, so we need cooling water. Yeah, so the cooling water can be taken from like this one. Yes, so we can take that from, for example, from the river. Yeah, which is as an open cycle, or it can also be as a closed cycle. Yeah, so usually if we have a power plant in which we have a cooling tower, so that means we have a closed cycle. Yeah, it means that the cooling water will be recirculated over and over. Yeah, so that we have a cooling water here. So the function of the cooling water is to cool down the cooling water. Yeah, because we know that when the cooling water is used in the condenser, so out of the condenser here, yeah, so this is the cooling water goes in through the condenser, and then it will receive heat from the steam. Yeah, so here the temperature is increasing. So what happens here in the cooling tower is that we give a mechanism to cool down the cooling water, and when the temperature is dropped, then we can recirculate back here into the condenser. So this is a closed cycle cooling system. All right, so yes, in general, this will look like this one, although more complex in real. Yeah, and this one as well. So this is in illustration in a block of equipments like this one. So this is actually similar to the one that we've seen before. So we see here that specifically in the boiler. So what the boiler looks like, yeah. So the boiler here, you have a boiler drum here. Yeah, we have a steam drum, and this is will be the the boiler or the combustion chamber here. Yeah, so usually called boiler is for the combustion chamber. Yes, so we call all of this, yeah, we call all of this as a boiler. So this will be a boiler. So there will be a combustion inside the boiler. So the boiler here is here. So we see here what happens here in the boiler. We have a tubes which is located around the wall. Yeah, around the wall of the combustion chamber in the boiler. Yeah, so we have a tube which is located in the in the sides of the wall here, so that when the coal is burned here, so that the heat will be absorbed by the tube, and then it will go up. Yeah, so we will see later that how is the mechanism, how is the process for the flow goes up. So this can use natural convection as well. Yeah, as the temperature increase and that it will change phase into vapor. So it means that the density will be lower, so that it will move directly up. Yeah, by using natural convection. Yeah, and then it will go into the steam drum. This is to collect the steam, and then the steam. If we have a water still, we have a water, so that will be directed down again to the water wall. So this is called the water wall. And the steam here, which is a full steam, yeah, so there will be no mixture again. So the steam here, we have a pot at the top here, so the steam will direct it through the superheater to become superheated vapor, and then it will go to the high pressure turbine and so on. Yeah, so they have from the high pressure turbine, we have reheater and so on. So you have seen this similar figure before in thermodynamics. Yeah. Okay, so this is combined cycle. We will learn about this in more detail as well. So this is a combination between the Brayton cycle or the gas turbine here, in which for the gas turbine, we have three components. What are the three components in gas turbine?
Low pressure turbine, intermediate pressure turbine, and high pressure turbine.
Really? Gas turbine? Yeah, in one turbine, it can consist of several stages. Yeah, several stages. But there are three components for the Brayton cycle. What are they? Brayton cycle? What is here? This is air going into the first.
I think it is compressor.
Yes, correct. So compressor, then?
Combustor.
Yeah, combustor and gas turbine. Yes, correct. So this is gas turbine.
Combustor.
Yeah. Yeah. So that is correct. Yeah. So Brayton cycle consists of three equipments. Yeah, three equipments: compressor, combustor, and gas turbine. So we see here that this is very similar. Yeah, the rest of here is very similar. But now the boiler here, in which we have the boiler, the coal which is directly used to heat the evaporator, the superheater, and economizer as before. Now put in a row like this one. So this becomes HRSG, or this is called heat recovery steam generator. Yeah, so it's recovering. So using the exhaust gas of this one. Yeah, using the exhaust gas of the GT, the gas turbine, because it's still high in temperature. So we utilize the exhaust gas here, yeah, in evaporator and so on. So the rest will be the same. Yeah, it will go into the Rankine cycle here. Yeah, so we have the turbine. It can be several stages of turbine. We have the condenser. We have the boiler feed pump, and this becomes the boiler, yeah, which is called HRSG itself. Yeah, so 4 components similar to before. Yeah. Okay, so this is for combined cycle power plant. So we will learn later about that as well. Yeah. Now this is how it looks like for the combined cycle power plant. Yeah. Basically, yeah, if you see this sort of building like this one, yeah, we see like so this will be combined cycle. So for example, if you go on Gresik, yeah, you can see the shape, yeah. So that is PLTTU. All right. And about gas turbine, I think you have learned this as well, yeah, before in the second thermodynamics, yeah. We have 3 main components: compressor, combustor, and exhaust, turbine here. Sorry, turbines. Yeah, so not this one. So 3 components. So this is the turbine. Yeah. So that, yeah, this can be used for airplane, yeah, turbojet, turbofan, yeah, or also turbo shaft or turboprop, yeah, and also it can be used for landed applications. So landed gas turbine is used for power plant, yeah. All right, so those in general what we are going to learn for this semester. So I think this is different source, so I'll just skip that on. Yeah, we have discussed a bit on that. Now, so this is the word sources and uses of energy. Yeah, so we see here that sources of energy, oil is about 35% of the availability of the energy. Coal, 23.5%, natural gas, combustible, biomass and waste, nuclear, hydroelectricity, and this is the other form of renewable energy. So quite small. Yeah. And this is the uses of energy. So domestic, commercial, and other 27%, industry 22%, power of heat or heat generation 20%, transportations about 20%, and energy industry use 10%, and the others. Yeah, so this is just as a knowledge to you. And this is the world energy consumption. So it's going to increase more and more. Yeah, more and more. All right, so this is the projection. Yeah. All right, so I think that will be for the introduction to this course. And for non-conventional, here we have hydroelectric. Now, particularly in Indonesia, Yeah, this is very important. We have many resources for water. Yeah, and the landmark is very suitable for this. Yeah. Now we will see the performance as well. Yeah, we will learn about the performance and how to uh, obtain to utilize the energy here. So this is in the form of potential energy, yeah, potential and kinetic energy. So actually for hydroelectric, there can be two, yeah. We can utilize high head or high potential, or we can also utilize high flow rate, yeah, or high capacity, such as in the river, yeah. So if you look at now in the river, we can, there are many turbine, micro hydro turbine that is developed, yeah, to utilize a very small head, but large capacity or large debit, yeah. Also biomass, so this is being developed as well. This is to substitute the need for the fossil fuel, yeah. We can use biogas, bioethanol, biodiesel, yeah, or from wood chips and so on. Wind energy, yeah, this is being developed as well. And this is what you are going to present later. Yeah. So we will divide that into groups. So you will describe the principle, the working principle. Yeah. The performance characteristic. And also what is the pros and cons. Yeah. What is the advantage and the disadvantages of this. So each of group will obtain a topic later. Yeah. Right. Then solar, yeah, solar energy. So this is from the sun. Yeah, there can be several way to utilize the solar energy. It can be in form of solar cell or photovoltaic cell. So that is converting directly to electricity with photovolts. Yeah, or we can also use like solar concentrating energy. So that's utilizing the heat, yeah, from the radiation of the sun. Yeah, so there are many ways to use the solar energy. So this is the example of solar panel. Yeah, so this is solar cell. And we have that now. Yeah, you can put that in for your house now. Yeah, for couples of millions, yeah, rupiahs. Yeah, for example, about 20 millions, yeah, 20 or 30 millions, you can build small solar panel for your house. Yeah, and also ocean thermal, another source of energy. Yeah, this is the example. Different temperature at different level or depth. Yeah, width as well. Yeah, and also geothermal. Okay, so I think that is what we are going to discuss. Yeah, and also nuclear. So that, yeah, this will be the task for you later. Yeah, so yeah, I will divide into groups, 9 groups in total. And about nuclear plant is actually based on the Rankine cycle as well. Yeah, so if we look at nuclear, so the difference is in the boiler. Yeah, in the boiler side. Well, this is also utilizing Rankine cycle. Okay, so I think that is all for today. So is there any questions? No questions. Okay, so if there is no questions, so we can close this class. And I'm really hoping that next week I can go offline. Yeah, hopefully everything is doing well. And I think most of you are in campus at the moment. Yeah, at the campus. Yeah, is it? All right. Yeah. All right. So okay, that's good. Very, very, very nice to see you. That you go to campus and following this class. Very good. All right. So I think that will be all for today. Thank you for joining this online class, and I hope we can see offline. Yeah, I can see you next week, inshallah. Yeah, about the time, is it possible to have at 9:45? I think some students have a class before. Yeah. All right. Yeah, we try to start at 9:45. We will see the situation as well. Yeah, whether the class is already empty or not. Yeah. But actually, for the first session, because it's if you take another course before, at 7 o'clock, so it should finish at 9:30. Yeah, because it's 3 credits of studies. It means that 50 minutes times 3, so that will be 150 minutes. So that should finish at 9:30 actually. Although in the schedule is 9:50. Yeah, because the schedule is based on ITS schedule. So ITS schedule is making every hour, 1 hour is 50 minutes, and that is taken one credits. So actually, if we take 3 credits in a row, so that means 2.5 hours. So it should finish at 9:30. Yeah. So I think we will try at 9:45. Okay. We'll try for that first and see how it goes. Yeah. All right. So I think that will be all for today. Thank you. And I'll close this class. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you.